I welcome Dr. John Felix Kumar, HOD, Department of Metallurgical and Materials Engineering, AJCE, man of immense knowledge and vision, to deliver the welcome speech. Welcome, sir.
Thank you. Good morning to you all. As head of the Department of Metallurgical and Materials Engineering, Jyothi College of Engineering, Kanjirapally, Kerala, I welcome you all today for this 58th National Metallurgist Day celebration. Our institute, Jyothi, is a Christian institution managed by the Catholic Diocese of Kanjirapally and the first new generation engineering college in Kerala to secure the prestigious NBA accreditation for prime departments and also NAC accreditation with A grade. Ours is the only college offering this unique branch of metallurgical and materials engineering in all over Kerala, other than NIT Calicut. We are today organizing a one-day educational program for school students on November 14 as a part of National Metallurgist Day. On this day, several awards are given by Ministry of Steel, Government of India, and Indian Institute of Metals to meritorious professionals in the field of material science and engineering. It is celebrated every year to commemorate the birth anniversary of Pandit Jawaharlal Nehru, our first Prime Minister. And this program includes quiz competition, technical events, and the main objective is to introduce the recent developments in material science, space technology, and nuclear sector to school students. Indeed, this year, today, we have a very special person among us, an outstanding scientist associated with Indian Space Research Organization. First of all, we seek blessings from our beloved Father Manager, Reverend Dr. Matthew Paikard. Father is always inspiring us with great support at every moment. Today, Father could not join us, he's very busy. Next, especially, we express our sincere thanks and welcome to Dr. S.C. Sharma, outstanding scientist, Associate Director, R&D, Vikram Sarabhai Space Center, ISRO Trivandrum, for agreeing to be a part of this event and to deliver inaugural address and talk. I welcome you, sir. We extend our warm welcome to our respected principal, Dr. Izzetpi Lakaparambal, to deliver presidential address. We welcome you, sir. We invite wholeheartedly our respected deans, head of the departments, faculty friends, Mr. Anurag, Student President, Syndicate of Metallurgical Engineers Student Association, and my dear students, I welcome you one and all. Thank you.
I welcome Dr. S.V. Lakaparambal, sir, Principal, Amal College of.
Good morning, everybody, and thank you, madam. It is my pleasure to be with you on this special day of a National Metallurgy Day. So, as Dr. John Felix was telling, it's an important day. It marks the birthday of our visionary Prime Minister, Jawaharlal Nehru also. As you all know, all visionary people, they have seen the importance of metallurgy. That is the reason that this particular day is he has promoted a lot of R&D activities and industries which require a lot of metallurgy involvement. As you all know, even the Indian Institute of Science, which is one of the premier education institute in India, this started with the metallurgy. And as the first engineering unit. And this is because of the visionary like J.R.D. Tate, who started that vision. I formally welcome Dr. S.C. Sharma, an eminent scientist in the field of metallurgy, for this webinar on behalf of Metallurgical College of Engineering. And it is my pleasure to be with you as the head of the institute and be part of this particular program. And I thank you for accepting to be with us for this program. And I extend a welcome to all the participants also and wish you good day. And if I look at the history of metallurgy, metallurgy deals with the subject of meeting the application with the less amount of material, having the property which is enough to meet the requirement. And I have seen one application in automobile field where the cam that rotates very fast and lesser weight cam is more attractive. Where they have that, especially the OD company, where that cam is coated with a cam has got a plastic cam but coated with a high strength carbon material, which makes it very lightweight as well as very strong on the surface, because that meets that particular application. And one advantage is that the energy used by that particular shaft is very low. That makes the vehicle very efficient. And if you look at the efficiency of the OD vehicle, not for this purpose, this alone, all other materials they use are very good. And because of that one, the efficiency of the power output from a 2-liter OD vehicle is much higher than 2.5-liter vehicle which we see in India. So these are some of the advantages you see when you deal with the very good materials in the field of mechanical and automobile engineering. And another important aspect of material science that goes into medical field, there also it should not create any problem for our body. And we have to do a lot of research to find suitable material for a medical field also. And I am dealing with the electrical and electronics engineering. And in electrical engineering, I have seen that we need materials, thin materials without eddy current, and which is achieved by material property, by processing of materials only in the field of iron. Similarly, in the electronics, as you know, the integrated circuits, they need materials which metals connecting to semiconductors at a very small size, so that a very good integrated circuit can be formulated out of that one. And these are the areas which I am somewhat familiar, and people work very much on that one. And this is a good opportunity to hear from our visionaries like Dr. S.C. SHARMA, who has got a lot of experience in dealing with the space materials in space technology. As you all know, that is a critical area for material science. In every material they choose, I believe that they have to do a lot of research in arriving at and using at that material. And with that immense knowledge in that area and the correct application area, we will be gaining a lot of knowledge from you, sir. And it is a really appreciable that we are able to get you for this on this important day. And I wish all the participants who are coming for this particular material learning process a good time, and wish you all the best. Thank you very much.
Thank you, sir. As per schedule, our manager, Reverend Father Dr. Matthew Picard, couldn't attend our meeting due to some inconvenience. So we are moving on. I welcome our chief guest, Dr. S.C. Sharma, an outstanding scientist, associate director, VSSC, ISRO, to inaugurate the National Metallurgist Day conducted by Department of Metallurgical and Materials Engineering, AJCE. We welcome you, sir.
Oh, thank you everybody, and greetings from me to everybody. Respected Principal, Amal Jyothi College of Engineering, Dr. J.V. Lakam Parambil, Dr. John Felix Kumar, Shri Anurag Chandra Mohanan, and all the participants of this today's celebrations and webinar. In fact, I remember my visit to college a few years back. I remember that time Mr. K. Shri Kumar, he was the head of the Department of Materials Engineering there. And I had got an opportunity to address the students in Amal Jyothi College of Engineering. And that memories are still fresh in my mind. First of all, that is journey to the college and the way it is located, the way it is designed, it is constructed. All those scenes are still very fresh in my knowledge, my memory. And I also share the memory of students. In fact, when this talk was going on, the way queries were coming from students, I was really impressed by the department. So thank you very much once again for giving me this opportunity. In fact, this National Metallurgist Day, as it was brought out by Dr. John Kumar, it is observed or celebrated mainly to on the occasion of our birth anniversary of our first Prime Minister, Shri Jawaharlal Nehru. In fact, he is the visionary or pioneer who has done greatest service to bring advancement or to initiate advancement in the country. The two major plans of Pandit Nehru, what he initiated, I will just share with you. One is 5-year plans. As you all may be knowing, earlier practice was there till few years back that we used to have 5-year plans, and every sector of economy, every sector of our society, we used to have planning for 5 years, what to do next 5 years, where we are lacking, where we are to go next. And this is because of reasons in systematic planning and implementation. Today, where we are, it is because of those planning. And second major thing, which as a material students of material science or all material scientists and professors of the department who are there, they will be really proud that he started this steel plants in the country. Actually, we were having one small plant that time initiated by Tata, that is now what is known TISCO. So that was there at the time of independence. But major this boost to this particular sector steel came when Pandit Nehru took initiative and he started the planning and implementation of various steel plants in the country. There's Bhilai steel plant, Rourkela steel plants. Actually, as in the case of IITs, we tied up with particular advanced country that time, like Germany or maybe say this USA. Similarly, for the steel plants also at that point of time, we joined with major advanced countries for each integrated steel plant, and these plants started coming up. And this gave a lot of boost to the advancement in the country. And you see the importance of this particular steel plant. I mean to say how much requirement was there. If I can recall that Rajiv Gandhi, he was addressing some audience when he became Prime Minister. He was addressing some audience abroad. And he was talking about the status, what we had at the time of independence. He told even one needle, needle, swing needle, what we have, it was imported at the time of independence. And today, where we are. So how much thirst has come to this area, really it is tremendous. But point is, see at that time, maybe at that point of time, these steel plants were very, very important. Even when we were doing our metallurgical studies in early 80s, these steel plants were very, very important. We were having 2 or 3 courses in this steel making, iron making. And we used to remember, our professor used to tell that the progress of a nation at that point of time was measured in terms of their steel production capability. More million tons of steel you are making means more advanced you are. That was the criteria. And we were just moderately making steel as far as production was concerned. Of course, we are now comparing with all advanced countries as far as steel production is concerned. But point is, as advancement took place, steel production of a country was no more the criteria of advancement. See, now a lot of new materials started coming and they started governing the economy, the progress of the society. So steels, of course, they are important, but they are not the measure of the advance of a country right now as it was earlier. And it has opened the field of so many new materials. Just now, our principal, Dr. Lakam Prambil was addressing, he was talking about new and new materials. So these new materials like electronic materials, your smart materials, functional materials, nanomaterials, biomaterials, biomimetic materials. So these materials, they are the yardstick right now for measuring the progress of a nation. See, any field, you just imagine, whether it is your personal life or whether it is in engineering or any other field of your life, materials play a governing role. Anything starts basically with materials. if you are having any concept, whether it is electrical or whether it is a mechanical area, you will definitely, your concept can be implemented if you are having adequate materials to implement it. So materials play extremely important role as far as every sphere of life is concerned. So please bear in mind, we are a very proud community of material scientists, and as a student of material science, you are a very proud place in the society you all are occupying. You are governing the progress of the whole technology or whole country as a whole. So this is one point. And further, really as a student, I would like to share with you, now so many opportunities available in the country. Actually, when you come out from your engineering college and when you start looking for what is next, now country is having so many opportunities in the field of material science. First is of course R&D, research and development. As it was brought out, our all major IITs are having courses in material science and engineering. NITs, they are having courses. And then of course, so many other places like Amal, Jyothi, what we have, this important course is being pursued. So this is just very vast open field for all of you now to pursue your higher studies. That is one aspect of your career, next career. And if you want to join job after coming out from here, so many tremendous opportunities are available in the country. Steel making, iron making, your copper smelting, then your aluminium melting, all those things are traditional metallurgical areas are there, they still remain. That is always are there. But new areas which are open for you now, see now, this electronic materials, you use your mobiles. And without mobile, you cannot imagine your life now. Even single day, you cannot imagine it in mobiles. So, most of the chips which are used basically for mobiles, they are imported right now. And electronic materials as a whole, if you take, we are depending to a large extent on imports. So now you will find in the coming years, lot of emphasis is coming in the field of electronic materials. You will find a lot of opportunities in this area. New foundries will be coming up there, where our government, even private sector, they are taking special steps. So new foundries will be there to make these electronic materials or single crystals, what you talk about, to make those particular materials for electronic applications. Electronic ceramics, that area now, even private companies, even entrepreneurs from IITs, in these special materials, they are coming forward and they are setting up industries, because for our space programs, we need these materials. And now we are finding many entrepreneurs, they have come forward from, pass out from IITs, NITs, from your regional engineering colleges, they are coming forward, they are setting their own small labs and meeting the requirement in specialized areas of the country. And then again, electronic materials, foundry is only one aspect for this single crystals or electronic materials. Even fabs, finally, you have to make chips from the single crystals electronic materials. And they are highly precise fabrication units, highly precise. They are under a very clean room environment. Clean room means the environment or the room in a hall where they are produced, there has to be a special environment. There has to be very clean environment. And even humidity has to be controlled. So those type of fabs, they are also coming up in the country in the coming years. And we have the scheme of Atmanirbhar Bharat. So a lot of planning, I can share with you, lot of last even 1 or 2 months, we had a lot of discussions all over the country. Core groups have been formed, how to meet, how to be self-reliant in these materials areas. So you will find that coming years or coming months for you very exciting for all of you. You will find lot of opportunities available for you to work and move further in your careers. And towards the last, actually, I will also invite all of you. We have our Vikram Sarabhai Space Center, which is very near to your place of location of engineering college. So whenever you visit time, actually now we are having difficult periods of this pandemic, but it will be not for always. So whenever you visit to Trivandrum, we are having one space museum where the history of our space programs and the idea or the view of our current programs, emerging programs, future programs, all have been put at one place, that is Space Museum. So whenever you visit to Trivandrum, just please inform and we will make arrangements to visit that Space Museum so that you can have a first-hand idea of our space programs. So with this, actually, I will wish once again all the best for this National Metallurgist Day and webinar. Thank you very much.
Thank you so much, sir. That was quite enlightening. Thank you, sir. Now I welcome Mr. Anurag Chandramohan, President, Syndicate of Metallurgical Engineers Association, AJCE, to deliver the vote of thanks.
Thank you, Presi. Good morning, everyone. Honorable Chief Guest, Dr. S.C. SHARMA, Principal, Dr. Z.B. Lakaparamban, sir, Manager, Reverend Dr. Matthew Paikard, our valued dignitaries, faculties, parents, and dear friends. It is my privilege to have been asked to propose a vote of thanks on this occasion. Let me begin by giving glory to the Almighty for making the event a resounding success. First and foremost, I thank our Chief Guest, Dr. S.C. SHARMA, Associate Director, VSSC Trivandrum, who wholeheartedly accepted our invitation to be a part of our event and for sharing his valuable knowledge with us. I thank our beloved Principal, Dr. Z.B. Lakaparamban, sir, for sharing his thoughts. Although we miss our dear manager, Reverend Dr. Matthew Paikard, his presence will always be good. I also extend my sincere gratitude to all the faculties, both departmental and non-departmental, for anchoring us through the events. A special mention to Father Ruben and Sebastian Sir, MCA, who have provided us with all the necessary online support. Without their presence, these events would have always remained as a dream. Thank you so much for your immense support, sir and Father. We all know an event like this cannot happen overnight. The wheels had started rolling weeks ago. We have been very fortunate enough to be backed by a team of excellent students. I'm short of words for the involvement and willingness. I'm extending my sincere gratitude to each and everyone who played their role successfully. Finally, I thank our budding stars who had made their presence in this event and who had successfully did impressive performance. Once again, I extend my wholehearted gratitude to each and everyone for being with us. Thank you.
Thank you, Anurag. Now we are moving on to our webinar session. All of you kindly mute your audio, and if you have any questions, please ask during the discussion session after the talk. I invite our dear HOD, Dr. John Felix Kumar, to introduce our chief guest, Dr. S.C. Sharma.
Thank you. I take this great opportunity to introduce our chief guest of the day, Dr. S.C. Sharma. He's an outstanding scientist, Associate Director, R&D Division, Vikram Sarabhai Space Center, ISRO, Trivandrum. He obtained his BE in Metallurgy from University of Roorkee and Master of Science from Indian Institute of Science, Bangalore, and PhD from Faculty of Science and Engineering, University of Kerala. He joined Vikram Sarabhai Space Center in 1982 and worked on physical metallurgy, heat treatment, and welding of ultra high-strength maraging steels, high-strength low alloy steels, special stainless grades of steels, and superalloys for Indian space programs. Subsequently, he had following responsibilities and contributions. As project leader, led the development program for a series of special purpose alloys for inertial navigation systems of launch vehicles and satellites. As head materials processing division and later as head special materials division, he guided the development of powder metallurgy products, ferrous and non-ferrous alloys, and complex investment castings for space applications. Also as group director, materials and metallurgy group, he steered the materials development program for ISRO, including high temperature materials such as ceramic matrix composites, ultra high temperature ceramics, thermal barrier coatings, ignition resistance coatings, etc. Also as a deputy director, VSSC, led R&D and product development activities in the areas of propellants, polymers, chemicals, and materials for various prestigious projects of ISRO. He presently is steering the entire research and development program of VSSC as associate director. Also as a visiting scientist, he visited an one-year project in German aerospace establishment, worked on non-equilibrium solidification of materials. SAR has published 128 technical papers in national and international journals and has 8 patents to his credit. He is the recipient of Metallurgist of the Year Award of Ministry of Steel and Mines, Government of India, Distinguished Alumnus Award of Indian Institute of Technology, Roorkee, ISRO Merit Award for Individual Excellence in R&D for Indian Space Program, Boswick Industrial Research Award, Fellowship of Indian National Academy of Engineering, Fellowship of the Indian Institute of Metals, also honored with the Certificate of Appreciation from International Astronautical Federation, IAF, for his outstanding contributions to the activities of IAF's Technical Committee on Microgravity Sciences and Processes as its member. With this brief introduction, I kindly invite Dr. Sharma to deliver Indian Space and lecture on Indian Space Program and the role of materials. I welcome you, sir.
Thank you, Dr. John Kumar. So I will now go to my presentation.
Yeah.
Yeah, has it come full screen?
Yeah, yes, sir. We can see.
Sorry for this inconvenience. So can we start now?
Yeah, please, sir. Please go ahead. No issues.
Okay, so good morning to you once again. So this is the title of my presentation, that is Indian Space Programs and Role of Materials. So I will be focusing first part of presentation on the programs of Indian Space Research Organization, and then the important role which materials have played in these programs I will share with you. So this is the total space program as a whole, how they look like. This slide talks about that. Actually, when we talk about space program, there are so many elements. We have space systems like satellites, launch vehicles, rockets. They are called all space systems. Then these systems are made of various technologies. Like we have your control components are there, the navigation components are there. Then we have materials are there, so all these subsystems basically they are called technologies which go into the main space systems. Then we have all these systems are meant for applications, very, very important aspects like telecommunication or remote sensing, weather forecasting. So another aspect of space program is space applications. And of course, without science, any technology cannot progress. So space science is very, very important aspect of the space program. Then of course, all our programs, they have to be for people. So we also have to think like how these applications, they can become a part of daily life of a common man. Then all these space systems, application technologies need some sort of industries, processing units. So this is also a natural part of our Indian space program. And all these systems, these technologies, these applications, they have to have management, and that for that purpose we need human resources, scientists, engineers, technicians, administrative people. And of course, our objective is that we have to develop end-to-end capability. We have to be self-reliant, Atmanirbhar Bharat. So this is our goal. And of course, over a period of time, we have developed huge assets. We started all our programs from a small place in Trivandrum, and now all over country, our programs have spread. So we are having huge assets all over the country. This is also a part of our program. And of course, our budget is very moderate. As you know, when we went to Mars, we used to say that going to Mars, 12-kilometer charges, even less than your auto charges, what we have in Trivandrum. So very moderate budget compared to other advanced nations like NASA or European Space Agency, very moderate budget we have. And of course, we have very strong outreach program. So today I am talking to you, this is also a part of our outreach program. And to have our advancement, to keep pace with the advancement with the advanced nations, we have to have international cooperation. So all these are the important aspects of our Indian space program, what we call Indian space program. Very interesting for all of you. See, this is the slide which shows how space programs started in India. So, you know, whenever you talk about ISRO, first thing comes in our mind, place name Tumba. So all these space programs basically originated Tumba, that is a place near Trivandrum. And why Tumba was selected? Because, you know, our geographical equator, it passes in Indian Ocean, which is few 100 kilometers away from your Kanyakumari. That is one important aspect of our Earth. but geomagnetic equator, which is very, very important for various space experiments, space physics experiments. That geomagnetic equator passes through Tumba. So this is the aspect which was kept in mind when Tumba was selected for Indian space programs in earlier 60s. And Tumba was at that time a small village where fishing activity used to be carried out at that point of time. And our Dr. Sarabhai, who is the father of Indian space programs, and Dr. Homi Bhabha, who is the father of atomic programs in India, both together, they came to Trivandrum in 1952, and they were aware that the geomagnetic equator passes through Tumba. So they came to Trivandrum and they had an inspection of the place. This is the photo shows they are doing inspection for various logistics, how they can be arranged for making Tumba as a space center. And this is Dr. Sarabhai. When he started the program in 60s, he used to say that our space program, they have to play a very, very important aspect. He used to say that we have to be second to none in the world as far as space technology is concerned for common man. So with this motive, space technology for the masses, that was the objective motive of our Indian space program when they started. And this is very interesting slide for all of you. These space programs, I told you Tumba, it was in a village that time, and there was no building to start the programs. So there was a church in the Tumba, and then this church was offered basically to start this space program. So Dr. Kalam, you must all heard of, he used to sit in this church building, and that is the way Indian space programs initiated in the beginning, early beginning, very early beginning. And now this space museum, what I was talking to you some time back, is to visit a space museum. So this is the church which has been now made as a space museum where our history and our future dreams all are presented in this museum, which is there in the church. And again, we had very humble beginning. We started, now we talk about your GSLV, very big rockets we talk about, GSLV, GSLV Mark III, all you must have heard of, PSLV, that is Polar Satellite Launch Vehicle, which is almost tens of meters of height and several tons of weight they can carry. But when we started with very small sounding rockets. Sounding rocket means it is a small rocket which can simply go 100 kilometers, 200 kilometers up from the surface of Earth, and it will carry some experiment. And once experiment is a payload, we call it, and then payload is ejected out from the rocket falls into sea. So that was the beginning, and it shows about various sounding rocket programs that time. We started with RS-200. You can see on this table here, that is Rohini series sounding rocket 200, which was the length of only your 3.6 meters. Just imagine, lift of weight was only 108 kilograms, and it carried a scientific payload of only 10 kilograms. It went only up to 85 kilometers up in the sky and came back. So this is what the first experiment in 60s was carried out in our space program. And then it had RS-300, 300 Mark II, 560. So this is the way these rockets, sounding rockets, started growing in size and weight. And this is Indian space program, how they look like now. We have on the left side of the screen, you will find SLV-3. That is Satellite Launch Vehicle 3, which was the first launch vehicle, satellite launch vehicle. That is next step from sounding rocket. This is the rocket which puts satellite into Earth's orbit. So this is SLV-3. This first flight took place in, I think, 1978, if I'm right there. And total weight of the rocket was 17 tons. And it carried 40 kilograms of one satellite into low Earth orbit. And the height of the total rocket was 22.7 meters. And Dr. APJ Abdul Kalam was the project director of this particular first launch vehicle of India. And today where we stand, we graduated to ASLV, that is Augmented Satellite Launch Vehicle, then Polar Satellite Launch Vehicle, then GSLV Mark 1 and 2, that is Geosynchronous Satellite Launch Vehicle. And today we have huge rocket with us that is called Geosynchronous Satellite Launch Vehicle GSLV Mark III. And it can take 629 tons of weight into the space. You just imagine SLV-3 17 tons, and we stand now 629 tons of rocket weight. and it can carry 4 tons, that is 4,000 kilograms of weight into geosynchronous transfer orbit. First rocket, GSLV-3, it went only 200 kilometers, maybe 300, 400 low Earth orbit, 300, 400 kilometers from the surface of Earth. But when we talk about GTO, that is geosynchronous transfer orbit, it is 36,000 kilometers up from the surface of Earth. So this is our capability which we have gained over the years. And total height of rocket, you can see here, is around 50 meters. There, what we stand now. And this is the how progress took place. We have first of all starting phase, that is in 1960s and 70s. Lot of infrastructure was built up. Then a lot of experiments were carried out, development activities were carried out, and then we entered in the 80s experimental phase. Like whatsoever things were getting developed in the laboratories, labs, they started coming into the field, and various developmental flights of rockets started taking place. And then in 90s, we entered into the operational phase. Our launch vehicles, they started becoming operational for services, like our PSLV. And then we have now our expansion phase, which currently we are under that expansion phase here. We have got now GSLV over PSLV, GSLV Mark III, new programs RLV. So this is the way these programs have grown over the years. And this, I was talking about huge assets of ISRO in the country. So this is now all over country, how various space establishments are there. You can say on the southernmost tip of India's map, you can say here Trivandrum, and where we have major center that is called Vikram Sarabhai Space Center. We also have Liquid Propulsion System Center here, ISRO initial units. And also we have Indian Institute of Space Science and Technology, that is the Educational Institute of ISRO. So Trivandrum is the major part of, it plays major role as far as ISRO is concerned, program is concerned. Then Bangalore, we have our satellite making center. Ahmedabad, where all applications are developed. And Harikota, that is on the in this your Bay of Bengal. Here we have our space port from where these rockets are launched. And all over country, we have the network of various natural resource mapping centers or your various ground stations, tracking stations. That network is spread all over country, as you can see here. So as you can see, this is the two major aspects of our space program, which you all daily read in the newspapers. And two major elements are Indian remote sensing. And second most important aspect, your national satellite system. So remote sensing, basically it is for carrying out various mapping operations of the earth. And then national satellite system, that is INSAT, it is basically for communication services in the country. So these two major systems of our Indian space program for application point of view. As you can see here, these are the applications of INSAT. Various applications have been shown here. This is your mobile satellite services, your business communications, TV broadcasting, data collection, then your meteorological services, disaster warning, telemedicine, development communications. All these services, these applications are managed through satellites under this INSAT series of applications. And this is another example of your village resource centers, how they come. You see these now remote areas in the country, very difficult to have access to these areas, but satellites, space programs, they make it possible. So through our satellites and putting our ground antennas in these remote places, our tele-education programs in the far-flung areas, tribal areas, then your drinking water, like you can carry out with the remote sensing satellites, you can do some sort of even underground mapping of water. So where are the potential sources of water, like in our desert areas? So those also can be, our satellites help in those things. Then telemedicine, where doctors, hospitals are not possible there. So these people get your medical advices, then your this type of services by doctors, well-known doctors who are sitting in cities and then big towns. And then training the people, skill development in villages. So satellites play a very, very important role in all these development programs of the country. This is the tele-education concept has been shown here. This is an interactive program. So various your modules, lecture modules are made, and these lecture modules are transmitted to the village resource center. There is a hall in a particular village there, where whether it is skill development or it is for the primary education, children, they get this sort of training in these centers through tele-education concept. And this is telemedicine. I already talked about you that whether we have concentration of mainly these services, our advanced services in the field of medicine, in the field of biology. They are basically concentrated mostly in big cities. But through our telemedicine concept, we are able to take these services to the villagers in remote areas too. And this is your search and rescue operations. Suppose some ship, basically it is in distress in deep sea. So how to communicate? It needs help. So it sends signals to satellite, and satellite transmits those signals to the ground, and then help is initiated for these applications. Similarly, this is your total network of our Indian regional navigational satellite system. As you can see, various satellites, how they make a constellation. It has been shown here. And these are the elements of Indian remote sensing satellite. That is the second major element of our Indian space program, that is called Indian remote sensing satellite network. So here you can say first this satellite under this program was launched in March 1988. And now so many satellites under this remote sensing, they have been put into orbit. Here various applications of remote sensing. This is agriculture. Like you can carry out some sort of, again, terrain mapping. And here you can find out where we are having wetland, where we are having some sort of your desert areas are there, where are the barren lands are there. So it helps basically in giving an idea to the planners in the country how to plan the best use of land available in the country. Like ocean, here also, as you can map this earth here, similarly you can also map ocean. So here, where are the potential fishing zones? You can find out using the satellites, various rays are transmitted, and then feedback comes back to satellite here, and then it is transmitted to your coastal areas, potential fishing zones in the sea. So this is the way now space programs, they have become a part of your national life. And this is how it helps basically in what is called, you're taking images for even defense applications. You know, if you are having some sort of your satellites with very high resolution and you can find out what is happening on Earth, your defense will be much more better. So we started basically our program where resolution was 360 meters, like 360 meters distance on the Earth can be seen or can be resolved by satellite in space. And now we have come to, this is also some time back, probably now even we are much better than even 1 meter of your resolution. So any activity which is taking place on Earth, or any establishment which is there on the Earth, and we can resolve up to a resolution better than 1 meter. So it gives a lot of very vital inputs to our security forces for our defense purposes. So in this way also we have built our capability, not only satellites, but even systems for that, where they can read these, they can take these images, camera technology. So all have been now put into country. This is Gateway of India, as you can see here. It is taken by our resource set 1. So the circle which is shown on the right hand side, you can clearly see this shows Gateway of India on the Bombay coast. And this is Begumpet Airport, Hyderabad, how clear picture has been taken. And this is UNO city, Vienna, Austria, how clear these things. They are all available basically now online. And this is Wasteland Mapping, like wherever I told you, by having this sort of mapping through space, we can find out where our land is not utilized properly. So we can reallocate our resources to these areas for better yield. This is potential fishing zones example here. We carry out some sort of thermal mapping of this water, ocean water, and that thermal mapping gives the idea where are more fish and where are less fish, and accordingly fishermen, they get periodical input from the government and they plan their fishing activity and come out with very productive results. And this is about our launch port. I told you that it is in Sharikota, that is in the Bay of Bengal. It is almost that is in Andhra Pradesh, but it is you can reach from Chennai also. Direct road links are there. So you can see this is the tall building. This is the launch pad from where these rockets. We have basically now 2 launch pads for these rockets, from where PSLV, GSLV, and these Mark III rockets are launched. So this has given you the idea about the space program, how they look like, where they were and where they have, what level they have come, how important and integral part of daily life they have become. But point is, see, materials have played a very, very important role in all these programs, in all these rockets, in all these systems, subsystems, applications. And when we talk about materials for space applications, you please bear in mind, it is a very, very difficult area, because here, when we talk about rocket, you have to have material which can simultaneously can be exposed to very low temperatures, sub-zero temperatures, cryogenic temperatures, that is minus even 150, 180 degrees centigrade. And at the same rocket, you will find that where the rocket action takes place, hot gases come out. You need materials which can withstand very high temperatures, so the order of 1500 degrees Celsius. So in a single system, we need materials of diverse requirement, and simultaneously we have to consider lot of criteria for applying these materials. And then all these because we work in a very, very strategic area. Anytime embargo may be there, we may be denied technology from the advanced countries. So important aspect when the material development activity take place in the country, in our labs, we also have to have very sincere efforts to indigenize these materials, to develop these materials in the country. So parallelly, we also develop and then produce these materials in the country itself. That is our endeavor. Now, to give an idea about the materials, how these materials figure in a rocket, very broadly, I will tell you. This is a geosynchronous satellite launch vehicle, GSLV. And here we are having various stages. When we talk about lower stages, as you can see here, we are having a core motor that is called our stage 1. And we have strap-ons on both the sides, as you can see here. Both the side strap-ons are there. These strap-ons here on the lower stages of rocket here, we need maximum thrust, maximum force which can take rocket up. So that is the reason we have very huge motors, and because they are huge motors based on solid propellant, we need very, very strong materials which can withstand this pressure which builds up in these huge motors. So when we talk about very, very strong materials, we first thinking comes in our mind is steel. So on the lower stages of rocket, you will find that your steels or heavy, they find good applications, good amount of applications. But as when we start going up and up in the rocket, second stage, third stage, where adequate thrust already has developed. Now the important aspect is speed. Rocket has to pick up the speed. So there we have to have materials which are basically, we talk about your liquid propellant systems, cryogenic propellant systems, which provide more speed to the rocket. And here we have to have less weight because the speed has to pick up. So here our focus is basically to have lightweight materials, low density materials like your titanium alloys, aluminum alloys, or magnesium alloys. And of course, then when we go to the uppermost part where our satellite is kept, there we are having our electronics bay, where various interfaces of rocket and satellites, they are kept in this electronics bay area. Your control systems are there, your navigation systems are there. So here we have some sort of your housings, which is made of magnesium alloy, where these electronic systems are housed. So this is it overall scenario of a rocket, how it looks like. And now I come to the what role we have played in development of these materials. I will give you only very broad idea. I know probably you will not have come to this stage of knowing all these aluminum alloys in detail. So for your information, in aluminum alloys, mainly there are 7,000 series. 7 series are there, starting from 1,000 to 7,000. So 1,000 is almost pure aluminum, which are basically for electrical applications. And as we start going up and up, we have various type of alloying elements and various type of applications. So 2000, that is 2x, what is shown here, 2x. This is the 2000 series of aluminum here, which is having very good strength. At the same time, they are weldable, and they can also withstand low temperatures, cryogenic temperatures. So this is 2000 series. And then 6000 series is good for our space applications because they are deep vacuum conditions, these things are there. And then 7000 is having very highest strength, but they have some limitations of your stress corrosion cracking, but they have very good strength. So probably where some short-term applications are there, where stress corrosion may not build up. So those applications we prefer 7000 series of aluminum alloys. So what I want to emphasize with you, that all these series of aluminum alloys development have taken place in Indian space program for applications. So, and then you also have two major streams of aluminum alloys. One is wrought aluminum alloys and then castable aluminum alloys. So both cast components and then wrought aluminum alloys, in both these streams, developments have taken place and products are available for our applications. This is various tempers of aluminum alloys. I will not, depending upon their heat treatment condition, their mechanical working condition, I will not dwell upon that. And see, little bit about what are the challenges in this processing these aluminum alloys. Actually, these aluminum alloys, they have low temperature eutectic elements. That is your zinc, copper, magnesium. So these eutectic elements, they basically have some sort of your, they try to basically precipitate or maybe tend towards the gain boundaries. So, and finally then incipient fusion sort of conditions may develop there. We have to avoid them. Then we have your high melting elements. So your melting temperatures or melting conditions have to take care of these high melting elements also. And of course, it has to be very pure. Impurities have to be very, very less. And it has to be very homogeneous. We are making an alloy which has to be very homogeneous. We have to have all what is called your highest grade of your properties. Uniformity has to be there. Grain size has to be small as possible there. Otherwise, it may create problem. And of course, when we carry out subsequently heat treatment, then homogenization, there should not be any segregation. No coring should take place in the structure. So all these are the challenges for the material scientists or metallurgists when they develop these aluminum alloys. And this shows about the capability what we have developed in the country over the years. Extruded products, basically wrought products. Then you have, then this is the various industries where these products are made, like extruded products, as you can see here, they are made in our Hindalco industries. Then your ordnance factories are there. And then master alloys, basically for these applications, they are processed in, we have Hindalco again, that is, and then we have, that is Hindustan Aluminium Company, and then we have NFTDC, that is in Hyderabad, Non-Ferrous Technology Development. And then this is making the master alloys for applications, and for electrical applications, pure aluminum, again, Hindustan Aluminium, then National Aluminium Company, NALCO, they are playing major roles. And of course, for secondary processing, also industries have come up, like we have now various forging industries in Hyderabad, and we have now industries, basically your HAL, Bangalore. Then of course, even this rolling facilities, Balco, one cast house has been set up. I mean to say, we have made very good progress as far as self-reliance, Atmanirbharta is concerned in this area in the country. And they are not traditional alloys, they are special alloys made for space applications. So you just know how much struggle it has to be there, where we require very small quantity. Suppose large quantity is there, you will find a lot of commercial applications are there, means a lot of private people are coming and putting the industries and then getting the what's our products coming out, getting the profit, and then fine, this is a part of natural process. But these materials are required in a small amount. So special efforts and industries will not come forward. So we have to persuade industry, we have to work shoulder to shoulder with industry, and then get these products for space applications. These are challenges. And this is the your heat treatment facility which has come up in Balco with the help of some 100 crores rupees investment was made in this facility. Similarly, this ring rolling, these various facilities has been established by ISRO in the country, like ring rolling mill, the ring expander, solution treatment facilities. So this shows about the infrastructure building exercise done by ISRO. And this is again shows some industries which have come in this area and they are established by ISRO. Again shows about drop bottom furnace or hydraulic forging press set up in the country. And this shows the picture. See, from where we started. Actually, we started one indigenization program, a special program we mounted for aluminum alloys. And you can see in 2002, we were almost 78%, we were importing these materials from abroad, and 22% was only the indigenous content. And right now, we have made almost indigenous progress, like 86% alloys are made in the country, only 14%, which are easily available in the international markets. We do not pose any challenges as far as indigenization is concerned. Those only are left out basically for import. So this is the way progress has been made. Similarly, in the case of titanium alloys, I will not go again in detail here. I mean to say that we are having three major categories of titanium alloys. As you may be knowing if you have read, we have an alpha, then alpha beta, and then beta. This is all depending upon the crystal structure for application. So all these categories of titanium alloys, we have made very good progress in the country in this titanium alloys. So these are the various products which have come out from this titanium alloys. Your propellant tanks, where your propellants, liquid propellants are stored and they are taken to space. Then they are again your half alloy titanium tubes, which has been made by our nuclear fuel complex Hyderabad. And this is welded gas bottle of titanium. You just imagine, first making the alloy, then getting the shape of the alloy, getting the required properties in the shape, and finally this welding operation, very, very important, critical, difficult operation, and finally it has to be tested. This is a pressure vessel basically. It has to go several hundreds of bars of pressure it has to withstand. So all that efforts you can visualize starting from the development to the application, how much difficult role is played by material scientists in this area. And again, in the case of titanium, our starting material for titanium for making alloy, that is called titanium sponge, was imported maybe around 15 years back. But now we have developed one plant. It has come up in Kerala itself, one place called Chavra near Kollam. This titanium sponge, 500 metric ton annual capacity, this plant has been set up with the help of ISRO here. We have become self-sufficient as far as the starting material of titanium is concerned. And this is the titanium sponge, as you can see on the right side top here. This is the sponge lump which has come out from the processing plant, and this is basically a chemical plant. Various steps or various or subsystems of the plant, they have been shown here. Similarly, I will talk you about the steels. We have talked about aluminum and titanium. In the case of steels also, we use in our space program marine steel, which is called ultra high strength steel basically. It has strength up to 1800 megapascal. Just imagine, it will be tied up to you. And in the country now, full-fledged, because these steel, they finally, big motor cases are made out of this steel, size as big as 3 meters of that size basically, and around meters long length. So first plates are made from the ingot, and then these plates are basically shaped, and then welding carried out, and getting the properties. I mean, heat treatment has to be carried out in these big products. All these facilities now available in the country, established in the country successfully. On the top, you are seeing the plate, which is being rolled at Rourkela steel plant, Rourkela. And then this is the motor case. This is the various segments of motor case. This is having 5 segments, which has been made out of this marine steel, ultra high strength marine steel. And we are also working using of your 15CDP6, that is called your high strength low alloy steel, HSLA. And for that, heat treatment is very critical. Such a big size of motor case has to be heat treated. So this is the heat treatment facility which has been established for this steel, special steel. Now again, very quickly I will go through. For titanium alloys, we have various products shown here. even ELI grade, that is called extra low interstitial for cryogenic temperatures, where temperatures of the order of minus 150 degrees centigrade. These allows find applications. And in the case of magnesium alloys, these are the electronic housings I was talking about there, these ones. And in the largest magnesium casting, and that is called your gimbal, basically axial gimbal casting, outer axial gimbal casting, which is almost 450 kilogram magnesium, such a huge casting in magnesium, single what is called time operation. So this huge casting also now has been, largest casting in the country, if I'm right, has been realized for our space applications for inertial system testing. Similarly, our non-metallic materials also find applications. Carbon cloth. This cloth can withstand very high temperatures and highly ablative environment. So this cloth is now developed in the Vikram Sarabhai Space Center lab first, and now industries have come up in Coimbatore and making this carbon cloth. And carbon cloth starting material is silica cloth. For that also now industry is available in the Chennai and making this silica cloth. And both these cloth are not only used for our space program, they are also used basically for your defense applications, for your missiles, what we talk about. So in thousands of meters of this cloth now is produced in the country. Similarly, permanent magnets, special materials, samarium cobalt, which is having very good magnetic product, because we cannot bear with any ordinary magnet. Otherwise, weight will be penalty. We need highest properties from the least amount of material, least amount of weight of material, least amount of volume of material. So that is the reason your samarium cobalt magnet technology, that is which is having very high magnetic product with small size of magnet, we can achieve very good force. So this material also now has been developed in the lab and now being used for our space applications. Similarly, powder metallurgy products, we are having liquid metallurgy, where we are making alloy in liquid form, then finally we are pouring into your molds and getting the ingots. That is one route. Similarly, our alloys, where difficult shapes are there, cannot achieve basically by liquid metallurgy route. So, or some special properties are required, like structure has to be porous in nature. So those type of applications are through powder metallurgy. You must have, definitely, if you are in your course, you must be having this course, powder metallurgy. So these powder metallurgy components also find applications in our space program. Here is shown nozzle throat insert, basically for your combustion chamber. This throats inserts based on graphite, they have been developed. And this is the brush blocks. Your electrical conductivity is very important, based on silver graphite by powder metallurgy route. And here again, very difficult components you can see here, made of copper. Complex components are there, and these here regenerative cooling concepts also is there, like your propellant before being used for combustion, it is made to cool these chambers. So this type of intricate applications also using these copper alloys have been developed. Titanium alloys, some more applications like bimetallic components. In the same your structure, one side you are having titanium, other side you are having aluminum alloys or steel. So that same component on two sides, two faces, it can cater to two environments simultaneously. Very difficult. How to bond these materials together? Both are having different characteristics. So various special bonding techniques like your diffusion bonding, solid state bonding, or we call about your explosive bonding. So these techniques have been developed to realize these bimetallic components for space applications. This is another some powder metallurgy components have been shown here. Again, seal rings. They are again basically dual layers they have. One side we are having one composition of powder, other side other composition of powder. Bilayered rings by powder metal applications, basically for your sealing purposes. This has been, and then similarly you have for high temperature applications, some sorts of sharp leading edges, high temperature applications made of ceramic materials, or ODS, that is oxide dispersed strengthened mechanically alloyed alloys. So these applications also now structures have been made and realized for our applications. So I will not be able to share you details today because time is not there. Maybe we can have some other time, we can share the more details about the what is called your development efforts which have gone into these materials, their processing aspects, their testing aspects. And similarly, in the case of electronic materials also, very good progress has been. Indigenization program now has given results in electronic. Various antennas, these are based on titanates or beryllium. And then your dielectric resonators, which is basically based on dielectric materials. And mostly they are by powder metallurgy technique. These small antennas. You know that in your telephone, mobile, what you have right now, it has basically one patch antenna. How it receives the communication? It has a patch antenna, which is based on a dielectric material. Now you will be glad to know that these sort of development also have these patch antennas. This development also has been successfully carried out in the labs of materials group in Vikram Sarabhai Space Center. Now we have talked about traditional materials so far. Probably quickly I will come to the next phase. What is next? What is challenges for the material scientists now in the coming years? So see, biggest challenges is now for material scientists is that as these services, they are becoming a part of daily life of common man. You cannot remain without mobile, you cannot remain without TV transmission, and you cannot remain without ATM, going to ATM, withdrawing money. So like that, numerous applications which have come now from the space services. So these space services, if they have become a part of daily life of a common man, they have to be cost effective. They have to be as cheap as possible so that people can use it, even common man can use it. So when we talk about this, making this technology cost effective, cheap, then comes how we can make it cheap. So what rockets now we have talked about, your PSLV, GSLV, they are one-time operation. They will go into space, serve their purpose, put satellite into orbit, and they fall back into sea. Whatsoever money we have invested in these rockets, these motors, all will finally going to the sea. So if we can reuse these rockets, then how much amount of money we can save? How much these programs can become, how much cost effectiveness will come in these programs? So that is the concept of reusable launch vehicle. But point is, and here the concept is coming, two stage to orbit, single stage to orbit. Just like a space plane, single stage to orbit. You simply take off from the ground, go into space, and then come back, single stage. SSTO, what we call about. TSTO means maybe two stages. One stage to begin with, one stage may fall down, and second stage will go up and come down on the Earth again. But point is, the biggest challenge because of the material scientists or space scientists as a whole is, when these reusable space vehicles, they enter the atmosphere after serving their purpose in space, then they have to again enter the atmosphere from deep vacuum of the space. Because when they go to space, they leave the atmosphere of space and they encounter the deep vacuum of space. But when they re-enter the atmosphere, see the fury of your friction forces. Several thousands of your degree centigrade, your temperatures rise take place on the structure of your satellites, of your space vehicle. So these space vehicles, reusable space vehicles, launch vehicles have to be protected from the fury of temperature. So here material scientists are playing a very, very important role to protect these reusable space vehicles from the fury of atmosphere during re-entry. And one experiment took place in 2007, you may remember, that is called Space Capsule Recovery Experiment. One small space capsule we took into space, and it re-entered into atmosphere, and it was recovered through sea. Finally, it made a splash into the Bay of Bengal, and it was retrieved. As you can see here, the whole thing is shown here. Through parachute, speed was brought down, and finally it had a splash on sea, and then from balloon was floated, and then it was recovered by using these small boats. So, and here we demonstrated number of technologies here. This is the, as you can see, this bottom part, as you can, the conical bottom, the float on the top, which is keeping this float, this space capsule, and this is black color, conical, this is a space capsule. So this space capsule was, when it was recovered, it was as virgin as it went into space from ground. So you can imagine our all thermal protection systems, which is there on the surface of this capsule, how effective it was. I'm coming to that very quickly. So this is on the left side, you can see conical structure, which is protected by black color space tiles. And this is after recovery, basically how it looks like. So here heat resistant tiles, they have played a very important role. And this is how it looks like after recovery. Here, of course, few tiles from the surface, they got chipped away, but they can be easily refurbished. But all your re-entry, atmospheric re-entry operations were performed successfully. Or your electronic houses, your control components, your communication components, your antennas, everything was safe when it reached on the ground. Very critical aspect of this successful technology. So this is how these tiles have been developed. Actually, I tell you the challenge again here the tiles, because space, anything you take into space, weight-wise, it is a penalty. If you can reduce this weight, then you are doing great service to the space system. So this, and we were giving for space capsule total budget, total mass budget, weight of capsule was only some 500, 600 kilogram. So our space material scientists were giving the target that you have to develop a tile which can protect this capsule with total weight of 70 or 80 kilogram. So that was the challenge. So finally they come up with silica based tile which is having density only 0.3 gram per cc, which can float easily on the water and which can protect these temperatures of around 1400 degrees Celsius. So this technology was successfully developed, and this is the process how these tiles were developed. Various process steps have been shown here. This is basically by soil gel process these tiles were developed, and this is testing aspect I want to share with you, because this single shot operation. So each and every aspect, your thermal conductivity, your what is called your specific heat of the material, and then mechanical properties, all those things have to be thoroughly tested. This is, and they have to be tested on ground conditions as well as in deep vacuum conditions of space. So all those tests with respect to physical properties were carried out. This is the vacuum chamber where test was carried out. And again, thermal conductivity, high temperature facilities are there for testing. And this is called oxyacetylene flame test. Like this is called thermal shock test. So when your tiles is developed, it is subjected to flame all of a sudden. So normally any normal your structure, ceramic structure which is very fragile, it will break. Because when you talk about thermal insulation, we have to talk about ceramic materials, not metallic materials. And these metallics are very fragile. And as you know, house you must be using your china clay or your what you call your cups and saucers, ceramic based. So the moment they fall from your hand, immediately they will break. So thermal shock also equally critical for this application. They should not break under thermal loads. So those tests were carried out there on the these tiles. Excuse me, just 1 minute. And as you can see here, these tiles, after carrying out all physical properties, characterization, thermal conductivity, specificate, mechanical properties, we have to get first-hand experience of the overall environment. So these tiles, we made a small panel where these tiles were mounted, and one rocket motor we put on ground static. We call it, we mounted in a fixture, and this motor was fired. So when motor was fired in a fixed condition, then hot gases started coming out from the nozzle. So all this tile structure was kept in the wake of that nozzle. So that full fury we can simulate on a space here. It shows that type of test being carried out on the tiles. Again, we need basically some sort of, it is not only your thermal environment, even your atmospheric drags are there, which take place there in addition to heat. So that test is carried out in your wind tunnels. So we did not have that time tunnel which can create this temperature as well as your aerodynamic conditions. Of course, we are having now world-class, this is I'm talking about 2005. So since then, we have got all world-class wind tunnels already established in our Vikram Space Center. But in 2005, we did not have this tunnel where this type of environment we can create. So this was taken to one lab in Italy and whole structure to get confidence. Subscale of this capsule was taken to Italy for carrying out this type of test on the space capsule, and test was successful. Again, it has to carry out, not only we are having mechanical loads, thermal loads, we also have acoustic loads. coming over that. So those type of loads also create these tiles are subjected to during test. And then for communication purposes, these tiles have to be basically transparent to various your radio waves. So those type of your test also, antenna test also are carried out on these tiles. And this is the mounting scheme of this tile, because tiles basically we are fixing on a metallic structure of capsule. So you can just appreciate your thermal expansion. Metallic materials expand a lot, but your ceramic materials expand very little. So when you are fixing these tiles, ceramic tiles, on the metallic substrate, which may be aluminum honeycomb of the capsule, then when the heat starts coming on the structure, these tiles will not expand much, but your aluminum structure will expand. And that will create basically a lot of force, stresses on the interface of these two materials, and these tiles may get chipped away. So for that also some special mounting schemes having some isolation pads, those were developed and which took away the strains which are coming there. And finally we got successful. And here you can say front wall temperature, these tiles, they were subjected to almost 1400 degrees centigrade on the front side, and they were so effective that on the back side temperature was even below than of the order of 150 degrees centigrade only, which is very which is within the limit of metallic materials they can withstand. So that is the effectiveness of these tiles for this application. And this is these tiles, how they look like for this application. Various, maybe say, various sizes and shapes, machining technology was developed for this. And this picture was taken from the rocket when it was going on. These tiles, this is the journey of rocket. From there itself, these pictures were taken. The tiles were intact, and one facility also has come up for making these tiles, because we need these tiles in big numbers. So one industry also has been now has come up in Chennai to make these tiles large numbers. But similarly, we first experiment was only space capsule, but it has to now augment. The space capsule has to be bigger, so that we can at some point of time carry our cargo, or maybe carry our more payloads, carry our passengers also. So there is a called reusable launch vehicle concept, RLV, which is called. So there also this experiment was carried out in 2018. That is called RLV technology demonstrator, when a small rocket, basically having the same aerodynamic shape of a RLV, was taken into space, and then it was brought back and recovered on Earth here. So here also your tiles were developed. And here tiles were not only your flat type of tiles, or maybe small the curvature. Here different complex shapes also of tiles were realized by machining technique. And wherever small, medium temperatures, there are these blankets on the lower side. You can see they were developed for that application. And this is the tiles basically where we are having temperatures around 1400 degrees centigrade. But on the sharp edges, temperatures are much higher. Of 2000 2500 degrees centigrade. There we have to use different material that is called carbon structure, we call it. And that carbon structure is very prone to oxidation. So their special coating based on silicon carbide was developed, and finally they were tested and qualified for this application. This is the details of that coating over the nose cone of your carbon structure. This is various tests, as I talked about, your arc jet test, combustion test. They were carried out basically on these coatings on carbon structure. And this is another important, I will share with you this application. This is called air breathing propulsion. A little bit about very briefly. See, now only few advanced countries working on this technology right now. This is very, very complex technology. And India is, I think, now almost 4th or 5th in this area in the world, which has successfully done experiment in this area. So actually, when we go up in the sky, we take fuel and propellant with us in the rocket to propel it up in the space. So suppose, and what is the fuel? Basically, we are having propellant and oxygen. Either we have to take liquid oxygen we take with us, or some other form of pure oxygen in the liquid form taken there. So there is a concept, if we can use oxygen available in atmosphere, because almost for a few tens of kilometers, this rocket will be into atmosphere where air is available in plenty. And there we require the maximum thrust, maximum fuel is consumed there only. So during that regime of flight, if we can take away the oxygen basically from the atmosphere and combine with the fuel and burn it, then tremendous weight saving can take place. You need not take that liquid oxygen tank with you, that your oxygen propellant tank with you. Take away oxygen from atmosphere and burn it. So here comes air breathing propulsion. That is called scramjet, ramjet concept you all must have heard of, but very, very complex technology, because here we are talking about Mach numbers of around 6 or even 10 Mach numbers, that is speed at 10 times speed of sound, or that type of numbers we are talking about. So what's our ignition has to take place, basically it has to take place in this is difficult environment, and to initiate this ignition and to sustain the flame in this environment, very, very difficult. And here this air breathing engine was tested experimentally in 2018 successfully, and we are now working further to augment this technology for our application. Fine, this structure of course was made of again high temperature materials, carbon based structures, and they were coated by silicon carbide to have oxidation protection at high temperatures. Various tests were carried out. Now further, see, when we talk about very quickly, when we talk about now space plane, these tiles and these carbon structures, they get damaged sometimes during re-entry. You must have heard about the accident which took place in the case of space shuttle, and there the main reason was one tile, silica tiles. It got chipped away from the structure, and finally it became the hottest zone for heat to enter, and then it created the catastrophe of the space shuttle. So people are working now basically for the more robust, more strong, sturdy thermal protection system. And here comes your concept like ultra high temperature ceramics. So the special type of ceramics are there. So those which is very, very strong, which can be used many times. No refurbishment is required when it comes back on the earth. So they are also now development. This is called, they are basically borides of zirconium and hafnium. So they are also now work, they are the powder metallurgy route mostly. So they are also now work has started, and various structures and microstructure characterization we have started doing. This test also has been, this thermal shock test, that's called arc jet test. So all those high temperature tests are carried out. This is again carbon structure, but here the advantage is it is foam, ultralight. So earlier we were talking about carbon nose cap, where the highest heat is coming. So we were using solid carbon, but if you can use foam carbon, weight will be almost 1/10 or even less than that for that application. Work is going on. This is foam getting tested under high temperature conditions. So this is the complete picture I have given you about space program, how they started, and what role materials have played. And we were earlier busy with developing some sort of traditional conventional materials, of course special materials as far as space is concerned, special, but very, very special materials. But then requirement graduated basically for going high temperature materials for thermal protection. And finally, temperatures became higher and higher, and we are now coming for still higher temperature materials we are developing here. So this is the vision of Indian space program. See, we started in 90s, early 90s with PSLV operational vehicle, and right now we are working we are having operational our GSLV Mark III, very big, gigantic rocket, and we are working on reusable launch vehicles. We are working on air breathing propulsion, and finally our aim is now to go for single stage to orbit. That is 2030 as we shown here. We have to realize our single stage to orbit, that is SSTO. Like as a space plane, we can take off from Earth, travel into space and come back on Earth here. So this will make not only our, this is also very important from the putting payload into point of view into space here. That is your how much cost effectiveness will come in the space services. So I hope I could share with you the programs and the idea behind the programs and about the materials as a whole. Thank you very much.
Thank you so much, sir. Your session was quite informative. So we got a better insight on Indian space research programs and the role of materials in them. And now we are moving on to our discussion part. Now it's time for discussion. All of you please unmute your mic and ask your queries if you have any, one at a time. If that's not possible, please ask your questions on the chat box.
Very good morning, sir.
Good morning.
So thank you very much for your wonderful, informative presentation to make awareness of our space activities. My question is that density is a major constraint for selecting the materials. Okay, so other than the density factors, what are the factors to be influencing for selecting the newer materials for to reduce the weight of the launch pad vehicles?
Okay, actually density very correctly you told, but along with density, we also have to have other properties. Like suppose it is for structural applications, we have to look for mechanical properties. So suppose any material with the less density, it can give better mechanical strength. So that is one combination of criteria we can have. Similarly, when we are talking about your thermal applications, so there your density has to be low, but it should have very good thermal properties for that application. So always it is a combination of properties along with density. Suppose it is for electronic applications, we have to look for low density. At the same time, very good electronic properties. It may be your dielectric properties. So this is the set of combination always play a part when we talk about density for space applications.
Is it find any difficulties? I think for going for a newer materials for particularly for launch pad vehicles. I think still now going with finding.
Yeah, it is full of challenge. It is full of challenge. See, first of all, when we talk about automobile steel, or we talk about steel for our ground applications, we have in our mind our stainless steels, is it not?
Yes, sir. Yes, sir.
That type of mild steel for most of the applications. Where your strength levels are around 400 Pascal or stainless steel, you can go even 1000 Pascal here. But then we have to, for our space applications, we have margin steel, where your mechanical properties in terms of strength, if we can say it is almost 1800 megapascal. It is almost double what we are using for our normal ground applications. But here again, margin steel, see, it is a combination of so many alloying elements.
Yes, sir.
And those alloying elements to realize that, I will tell you the very interesting story again here, how this margin steel came into. Actually, this is the steel, margin steel, where Pakistan nuclear scientist was caught.
Oh.
You remember?
Yes, sir. Yes, sir. Yes, sir.
He was caught stealing the technology of making steel. That was margin steel only.
Oh.
So this margin steel technology, how we basically mastered. In 70s, we started doing melting experiment on button level.
Oh.
We are having our arc melting furnaces there. So a small button, maybe 50 gram, 100 gram buttons we were making. And then we did not have any major melting facility at a high scale in the country. So Vishnu Dhatu Nigam, Vidhani we call it, that came in the country, that is a defense establishment, came in Hyderabad. So finally this button melting technology was scaled up and Vidhani came into picture and then started making the margin steel. So it is basically made by your vacuum techniques. It is made there. Secondary processing is very, very difficult here. Finally, it has to be welded for that application. Your motor cases, welding technology is so critical. I remember that point of time, 3 teams, 2 teams in VSSC and 1 team basically in Welding Research Institute, BHEL, Trivandrum. 3 teams were working to develop only welding technology because so many issues were coming. Your brittleness in the structure there. And so this is the way development take place. And these are the challenges in the development.
Yes, obviously, if the temperature difference comes in, evidently the properties will be definitely instantly it will change, sir, to make the disaster.
Exactly. Yeah, similar challenges there. Other areas also with the electronic materials, aluminum. Similar challenges are there.
Yes, sir. Thank you very much, sir. Thank you, sir.
And actually, if it is for your automobile application, other ground applications, so many labs will be working in the country. But because it is for specialized applications, all work has been carried out by a small team of dedicated material scientists.
Yeah. So thank you very much, sir. Thank you very much, sir. Yeah, myself honored for it.
Thank you.
Yes.
Is there any questions? So due to time constraint, we'll end up the session if there are no questions.
Okay, thank you so much for giving me this opportunity once again.
Thank you, sir, for the precious moment you have joined with us today. Deepavali today, actually. First of all, we wish you happy Deepavali, everybody also.
Oh, thank you. I wish you all the
Today,
same.
yeah, today. So thank you, sir, for the wonderful talk. It started with the rocket science, satellite mapping, and even potential fishing, and about the considerable material development for structural materials for space satellites, and usage and even production of aluminum alloys, starting from the production and the homogeneity of aerospace grade aluminum alloys. And also he talked about this, even the magnetic materials for space applications like samarium, cobalt, even dielectric materials like barium, titanate, the role of materials in re-entry and reusable purposes, even silicon, carbide coated, carbon reinforced composites, the whole gamut of materials we have got knowledge about it from your talk. So on behalf of Department of Metallurgical and Materials Engineering, Jyothi College of Engineering, and on my own behalf, I wholeheartedly thank you, sir. Thank you so much.
Thank you once again.
Thank you, sir.
Okay. Okay, go ahead.
As part of National Metallurgist Day, we have conducted a number of events in association. Now it's a time to announce the result of the event conducted. Anash?
Hello, Presi.
Okay.
Okay.
So our
Hello,
first
Avinash.
event was
Presi, proceed, please.
okay. Our first event was photography. Event name was capture, and the first winner is Kevin Samuel Jacob, St. Joseph College of Communication. Second goes to Smriti Diaz, Chabatigiri English School, Anjal Kollam.
Congratulations,
event was-
congratulations, Kevin and Smriti.
Next event was Ludo, and the first goes to Alan Saji, St. Thomas HSS, Erumeli. Second goes to Ardra B, Muthoot Institute of Technology and Science. Congratulations.
Congrats.
Next event was art. The theme was life in lockdown. The first goes to Amina Shifas, St. Thomas HSS, Erumeli. Second goes to Nishant M, St. Joseph College of Communication, Chenganashiri. Next event was poster designing. First goes to Alan V. Jose, St. Joseph College, Pala. And the second, Harida Ajit, St. Joseph College of Pala. The next event is auction. First goes to Fabian Maman and team. Second goes to Rohit V and team. So the last event was Alpha Hunt. The first goes to Angit Biju, Ursulan English Medium School. The second goes to Devang SR, Ursulan English Medium School. And we have two more events which is going on. The one is JCJ Memorial Quiz, and they have 6 participants. And at the final rounds, they are Aryanda G from Bharatiya Vidya Bhavan, Kozhikode. And the second one is Richard from Chavra CMI Public School, Pala. Asna PA, St. Thomas HSS, Erumeli. Arjun S. Nair, Anthony's Public School, Anakal. Adityan from Government VHS, Nekkad. From next one is Gautam Kiran, Sarvodaya Central Vidyalaya. All the best for the final participants. And that was all about the results. By that note, we are going to conclude our program. We all know that National Metallurgist Day is conducted on the birthday of our Honorable Prime Minister Jawaharlal Nehru. He once quoted that time is not measured by the passing of years, but by what one does, what one feels, and what one achieves. So let's live our lives being worth of time. By this note, let's conclude our celebrations on the 58th National Metallurgist Day. Thank you, everyone, and have a nice day.
Thank you all.
Thank you everyone for the auspicious event as president of